Alrighty, let's get started. Welcome to week one of the IEEE PCB design workshop. We're starting this a little bit later than we usually do. Usually we do this around like the third week of the semester, but we are in week, I don't know, 5 or 6, maybe even later. I've lost track of time. But this is basically a slightly condensed version of what we've done before. So in the past we've done a couple more sessions that are more lecture based before going into soldering, but this time we're just going to go straight into soldering without a break in between. So it should go a little bit faster, hopefully ends before your finals start. That's the goal. And if there's any delays, please keep track of any email announcements that I will send out. So my name is Adrian Sucahyo. I am a current master's student in electrical engineering. I'm also the chair of the IEEE Student Group. I've taught this workshop last semester and 2 other times before that to some extent. So I'm adapting some of the work that we've done in the past. So just a brief outline of what we're going to be doing. Here's our schedule. It's also posted on our GitHub. That should be in the email that I've sent you. If not, it's linked at the end of this presentation. Has anyone not received my emails? Because I sent one out earlier today. I will get you on, have you seen the RSVP link?
I did get that.
Okay. If you filled it out, your email that you listed should get an email from me. If not, we can figure stuff out after. So yeah, that's where a lot of the announcements will be, just to keep track of all the things. So here's our current schedule. I do recommend attending as many workshops as possible because they're trying to build off of basically all the previous material that you learned in the past. So show up and be here. If not, I am recording this, which is what I was trying to set up a little bit earlier. So hopefully, if you do miss a class or one of these sessions, you can just catch up, even speed me on one time to speed if you're into that. So we're going to be building a USB-C breadboard power supply. This is the same project we did last semester. It's a good design because it's relatively simple, but it's also something that you can use in your lab. So for those of you who are in the ECE department, you're familiar with breadboards, and you're powering those off of batteries sometimes in your circuits classes. This is something that you can just plug into your breadboard and use instead of one of those battery sources. So it's pretty fun. It's a surface mount project, so those of you who have maybe made boards in the past, have done through-hole, this is your first step into some surface mount soldering. It's not too bad. So some logistics. We will not need to charge a fee, so you can just get the board that we will be making. We did get our ASU allocation, which is a benefit of starting this a little bit later. We kind of know what's going to happen. And also, the other thing is, if you want to design your own board, so if you want to just learn how to use the software but don't want to make the USB-C power supply, you can design your own circuit and submit it to us, and we can get it manufactured as well. Just make sure you hit it by a certain deadline. I haven't set that yet, but I will announce it when that happens. And if you ever want to discuss any projects, I'm more than willing to chat with you. Also, more experience. I will shield the FSAE racing team. I'm a track team lead there with another individual who also helped teach this workshop in the past. We do board design on one of the teams, so we do low voltage and high voltage. So if you're ever interested, there's the Discord link. The track team meets on Wednesday, so actually tomorrow at 5:30, I believe. Just show up, and if you're interested, we do low voltage, high voltage, and there's plenty of PCB projects that we're still in the works right now. So if you want to get more experience, here's an opportunity too. Finally, here's the IEEE Discord. If you're in it, great. If you're not, no worries. It's pretty dead. Sometimes I put announcements, sometimes I don't. Most of the announcements for this workshop will be through the email chains that I'll keep sending out through the semester. So any questions before we get started? No? All right. And if you miss any of these links, QR codes, all this is posted on the GitHub as well. So, what is a schematic? How many of you are ECE majors? Good majority. Almost everyone. I think everyone. I maybe missed a couple of you. I'm very blind. But you've all seen schematics in your circuits classes. These are very critical to get right because these are basically the first step up from the block diagram. This is where you actually select all your different components that are part of a circuit. These are all the connections as well. So anything that's made in this representation will be translated into your physical representation. But what's important to note is that schematics are not a physical representation in the way that they're formed on a page. So you can have your components splattered all over this page, but they will look nothing like they will on the PCB. Use that to your advantage because it will help you basically create more logically organized circuits and schematics, so it's easier for someone to read instead of following the physical footprint, which might be a lot more terse to decode. So as many of your ECE majors probably recognize a lot of these symbols. Every electrical component will have its own symbol within the schematic. So all the pins that will be represented for each component you'll be putting on there will be represented in Altium or KiCAD or wherever. It may have some extra information, so like different inputs, I/O might have a different symbol, but they're relatively consistent across all your different platforms. Sometimes you don't even need to denote what type of pin it is, but it could be useful if you are doing some very complicated designs where pin hierarchies are something you need to pay attention to. So symbols. In your circuits classes, you might be familiar with just drawing a capacitor and putting a number next to it. So this is a 100 microfarad capacitor, this is 10, this is a resistor at 100 ohms. In software like Altium or KiCAD, you're going to be representing these with an additional designator. This is going to be like a little number. Each part will have its own like little letter to denote it. So capacitors are denoted with C. U's are for like ICs or miscellaneous stuff. J's for like jacks or connectors. There's a whole bunch of things. You can put part names. Pins sometimes have names as well that you can denote, and the pin numbers. Not all of them will have all of these attributes, but typically you'll be able to assign these when you actually make these. There's also a slight difference between US and international standards. In your circuits classes, at least here, we've been taught resistor is a squiggly line. Internationally, it's not the same. Sometimes you'll see a squiggly line, sometimes you'll see a box, which here represents impedance. Just get used to it. It's unfortunate that we have two different standards, but it's just how we do it. So there's a couple examples of basically some of the symbols that you'll see. Just reading more and more schematics will help you recognize the different nuances between them. Some people mix them because they're pulling from different part libraries, which have US and international sources. So any questions so far on schematics? No, all good? All right, nets and nodes. So the dot. In your circuits classes, you draw your dots, right? On your circuits, hopefully. Dots indicate a connection. In your software, if there's no dot, it's not connected. Sometimes it's hard to tell. So if you look at the image on the right, there's that little hop over. That's not default in Altium. I'm not sure if it's default in KiCAD either. Make sure if you need a connection, you put a dot between that, because that means your lines will actually be your nodes will actually be connected. There are times where you'll cross a line and there's no dot, but you think they're connected, and you translate it to a PCB, they're not connected. Any error in the schematic sheet will be translated to your PCB. There's another thing to help with organization. It's called net labels. So instead of having to draw a lot of lines crisscrossing across your PCB, especially if you have multiple like buses or a lot of different connections that are going to wildly different places, you can use something called a net label. These essentially allow you to make the electrical connection without having to physically draw the line between the component. It's very useful for power labels. So if you have like VCC, plus 5 volts, minus 5 volts, ground, those are all power labels. Those will all be connected electrically, but they won't look physically connected. So you can save on a couple lines across your page. And a lot of these, like you see USART, LED indicators, those are going to another part of the sheet, or the LEDs or whatever that USART bus is connected to. Those are where they're going to be allocated to electrically, but they don't look connected here. It's also useful for hierarchical design, which is not something we'll talk about in this course, but it's another way of organizing more complex designs across multiple sheets, sometimes with hierarchies, so you can have repeated nodes across multiple things. So, good schematic practice is key. You need to make sure someone can read your schematic. That's not readable. If you submit something like that at work, you're fired. That's not okay. So basically, you read a schematic like you read a textbook or any type of book in general. People read in the West, left to right. So your schematic should be organized logically, left to right. Most data sheets that you'll be able to read will be organized this way, some of them better than others. Because if your schematic is spaghetti, you're more prone to an error at this stage, and this is not where you want to make your errors. You want to make your errors in the layout stage, because that's actually something you can fix later on. This is kind of, no, don't do that. So, just to summarize, read left to right. Don't overcrowd. You have a piece of paper that is digital. Use as much space as you need. You can make that really large. Like the schematic sheet editor can be 1 meter by 1 meter if you wanted to. Don't actually do that, but you can. Use logical blocks. So if different components are related to each other in a certain function, basically group them together. Don't put them scrawled all across the sheet. And reference the manufacturer data sheets. There's a lot of reference designs in a lot of components because the manufacturer wants you to use their part. Follow their example. Typically, you'll have like a little design guidelines of how they actually came up with like some of the component values. Sometimes it'll just be a symbolic representation. Follow that. It'll make it a lot easier for people to recognize, because another tip is as you do this more and more, there'll be certain patterns you can recognize, like, oh, this structure is a reverse polarity protection. This structure is a linear regulator. People draw those certain ways, and if you draw to that same way, people will be able to read your stuff a lot quicker and understand your problem much faster. Label your signals. Sometimes it's not necessary, but sometimes if it's like an important, like this is the output of an amplifier, you can put a label on there, it doesn't hurt. And then power sources, power goes from top to bottom. So you put your VCC at the top, ground at the bottom. I've seen designs where they flip the ground up. Don't do that, that's kind of weird. I will judge you for that, but it's not illegal. Please don't. So, some examples. Who can tell me what is wrong with this one on the left? Don't mind those little X's, those are error suppressors. Anyone? I don't bite. Engineers are, oh.
It's like it branches out.
Yeah, so it's like kind of messy. It's kind of goes like out this way and out that way. What else about it is kind of weird? Correct, ignore the values. Yeah.
Orientation of the components is all over the place.
Yes. So if you look at this schematic, that resistor is horizontal while everything else is kind of vertical. That's weird. That doesn't need to be that way. This resistor can be translated vertically like that. These capacitors don't need to be vertical. Those can be horizontal. So that's the main thing. You can align a lot of your components together just to make it a lot neater. So what's wrong with the middle one?
It's all like too close together.
Yeah, it's bunched up. As I said earlier, infinite canvas, spread them out. There's no reason why you should ever be drawing something this tiny unless like it's absolutely necessary and you're trying to meet like some weird design constraint. Another thing I will point out here, this node, this cross right here, is right on this component's pin. So a component will have like the two leads coming off the end in the schematic editor. Typically, you don't want to put those on a node because it's kind of hard to tell, like, oh, that's where the component ends. So you typically slide it out, kind of like this one on the right-hand side. That one, pretty much okay. There's no major issues with it. So you can see how these components, the top resistors are aligned together, so they're nice and easy to read. Capacitors are flipped sideways, so you know things can flow correctly. This is some Class B amplifier. I don't remember exactly. And then you can read it left to right. Input, output. If you flip them, that's not to convention. People will be able to understand it, but it's weird. Don't do that. So things flow logically left to right. So any questions about this example? Nope, all good. All right. So I mentioned earlier, We're doing Altium, not ECAD. So Altium is from a family of softwares called ECAD, or Electronic Computer Aided Design, which are used to create schematic layouts and PCBs. There's a whole bunch of them. So there's like Altium, KiCAD, Eagle. I have things about Eagle, OrCAD, and EasyEDA. There's probably a couple more out there that I haven't seen before, but these are some of the main ones you might see as you're in college. So why did I choose Altium? Altium is pretty commonly used in the industry for doing like more complex circuit design or PCB assembly. It's something that you won't have access to as a hobbyist. If you're outside of school and not a student, you can't get a license. The licenses are like $1,000. Use it while you're a student, so you can gain those skills, and you can put this on your resume. The job market is not looking too hot. Pad your resume with as many skills as possible. This is attractive. Apparently John Davies was talking to some people at the career fair and said if there are people who know PCB design, they would hire them on the spot. You know, facetiously, but you know, it's a good skill to have. It's just like putting, I know how to use Git as an electrical engineer. It's kind of stuff like that. So, going on to the project introduction, this is what we're building. It's a USB-C breadboard power supply. There's basically two independent switching supplies that can be isolated between a single or dual sources. So you'll be able to use there's a physical switch on the board that you'll switch between the two. And then it has a USB PD trigger board, so you'll be able to use your laptop's USB-C power supply or some PD-enabled USB-C supply, and it'll give you the full 20 volts is what it'll try and put you at. And then there's an additional DC barrel jack in case you don't have a DC supply. You can just use some wall board. And then there's some output bleeder resistors, so there's capacitors, drain. So the block diagram for this is kind of like this. On the left-hand side, we read left to right. You can see all the different power inputs, and then you have this power input select. This is just a switch. It's a big purple box. And then those will basically, this block will determine how the power flows through the different switching regulators, and you get two different power outputs. If you are doing your own design, I would recommend blocking out what you're trying to design, just so you can plan for it. This is down in draw.io. It's a free little software. It's neat to use. And it makes your projects look a little bit more professional sometimes. So the power inputs, we're using some we're using some terminal blocks that you can just plug into your power supplies, DC barrel jack, USB-C, and you can put up to 20 volts on it. That's what our components are rated for. You can design these for higher voltage, but the components that we have selected for this project are rated to 20 volts, or not exactly 20 volts, but that's what I'd recommend. And then you'll be able to select your input with a switch. So you can either isolate the two A and B supplies, or you can power them off a single input supply and get two different voltage outputs. The switching supplies we're using is this LM2596. It's a buck converter. It's a monolithic little part that you don't really need to spec too much about because some switching supplies are complicated. So it's about 3 amp capacity, and the reference data sheet provides this lovely diagram. And this is what you're going to be creating in your software. So the data sheet is linked in the GitHub. You can also just look up this part number and look at any data sheet. There's a couple manufacturers that make it, but this is what it will look like. And then the power outputs are basically 2 terminal blocks, and then there's pin headers. They're not populated in this 3D render, but essentially you'll put some pin headers in those, and they'll just slot right into your breadboard power rails, and then you'll just have some power supply. Your PCB will plug right into your breadboard, so you have a power supply for your board. And then some output bleeder resistors, just so those output capacitors drain their voltage, so it's a little bit more stable. So any questions? Nope? All right. Go to GitHub, and you can download today's project files. We're going to be using Altium for now, because that's what I have. But if you have KiCAD, those are also available. So let me share my screen. All right. Alrighty. Hopefully y'all were able to open Altium or KiCAD. So we're going to start by creating a new project. There weren't really resources to download. per se, but there is that example schematic sheet if you were able to find that. So what I'm going to do is from this home page, you're going to create a new project. So you go to New, and you're going to click on Project. And that should open up an additional dialog window. And then this dialog window, we're going to just create an empty PCB project. There are a couple defaults in here, so if you have a multi-board project or you have like a specific format, you'll be able to like save them here. But for now, we're just going to do basic blank project. And the project name, we're going to call it something memorable. You can call it whatever you want. I'm going to call it USB power supply. And that's all you really need to do at this stage. There are a couple parameters in here you can add, but for now, this is all you really need to do. So once you have that, click Create, and then it will think for a little bit, and you should get something to pop up on the left-hand side. All right. So now I have this little project up here. So on the left-hand side, typically by default, you should be on the Projects tab. If someone doesn't see that, let me know. It might be a little configuration issue. But here's basically where all your project files are going to be found. It's basically how your project is organized. So at the very top is going to be something with a PRJ PCB file extension. That means this is a PCB project. There's going to be different files in here that we'll add as we go along, and each of those is a different thing. So what we're going to do is we're going to add a schematic sheet. This is the first step in basically making a PCB, which is placing your components down and connecting them electrically. So what we're going to do is we're going to right-click on this, or double-click, right-click, and you add new to project, and you're going to click schematic. And then you should get this to pop up. And you get a little blank sheet. This is your editor. I would recommend having a mouse because with any CAD software, touchpad kind of sucks. So if you have a mouse, bring it. If you don't, I'm sorry. So yeah. In this, we're going to be able to place all the different components that we want. And what I'm going to do first is I'm going to save this project somewhere just to demonstrate how that works, because some people will lose their project if they don't. So here, if you look on the left-hand side, there's two little page things that are red. That means they're not saved. When they're saved, they will be white. So here, I'm going to save these files. So you can just right-click and save. And then you can save it somewhere. By default, it will save wherever your Altium installation is, but you can move this out to somewhere else, so I can put this like in my documents folder, and then I'll just create a new folder for that. So this is demo proj. So it's saving the schematic sheet. I'm going to save this, and I'm going to name it USB. Oh my goodness, PSU. And then I save that. So that saves this document, and then this top one also should have saved as well. If you see save to server, it's trying to save to a Git repository. We're not going to do version control today, but if you want to do version control, it is totally possible in Altium, just like in KiCAD. So, has everyone gotten to this stage? Good? Okay. So in this stage, there's going to be a toolbar at the top. This is what you're going to be interacting with the most. There are keyboard shortcuts for this, but those you can learn those later. First off, let's look at these different symbols. So the first one over here is like the selection filter. If you click on this, all these different things are basically how you determine what you're going to be clicking on. So there's like components, wires, buses, symbols. Typically, you're not going to be using this very much in the schematic editor, but you're going to be using this a lot in the PCB layout stage. These other ones are just like little mouse movements, dragging and moving. Your selection tool. This is for alignment. So if you have a bunch of components You can align them together. Typically, you're not really using this in the schematic editor too much either, just because everything already snaps to a grid. In the layout editor, this will be a pretty important thing to use if you're doing a lot of things that need to be like horizontally or vertically aligned. Next to it is place part. This one, if you click on it, initially will bring up this window on the side, which is all these different components. But these are generic simulation components. These aren't actually the specific components we're going to be using today, so I'll show you how to get those components that we're going to be using later. Next to that is the wire tool. This wire tool is kind of self-explanatory. You click it, and now I can draw a wire on my schematic editor. So you do that by clicking, and everywhere you click, it'll basically plot itself, and then to cancel or to confirm, you right-click, and then it draws it. So I'm going to get rid of that. And then next to it is this symbol. This is for different ports. So you can see like there's ground, there's VCC, 5 volts, and a couple other symbols for your other types of grounds, like this is an earth ground. You can change what these say. So let's say you had a 3.3 volt power supply rail. This says 5 volts. You can double click on it and type 3.3. All of these will have a different editor, so I'll show you the properties window on a lot more things in a little bit. There's also the net label, which I mentioned beforehand, which is you right-click on the little wire symbol and you click net label. This will basically attach this little tool to your cursor, and in here you can just type in whatever you want that to be. And you would attach these to a different wire if you had some on the board like that. So now this is assigned to that wire. There's a couple other things like harnesses and different sheet symbols. We're not going to be using that this time, but those are things you can learn. Same with ports, we're not going to be using those. And then the other things is like you can put text and strings. So if you have text you want to put down, you can type stuff on there. There's some text. There's also a useful one, which is the note. So this is basically a sticky note that you put on your schematic. If you have anything specific you want to reference for later, type it in here. It's a sticky note, and I believe you can collapse them as well. So if you don't want them showing, you just make them go away. So those are the basic tools of the schematic editor. And now I'm going to show you how to basically import your components that we're going to be using. So Altium pulls your components from something called a library. Same thing in KiCAD. There's a little bit different import process, but for now I'm just going to demonstrate the Altium one. So in the GitHub, if you go to Master Design Reference Files, there's this Altium component library folder, and this has another folder inside for some reason. This is basically all we need for our PCB library, or our component library. So if you have this downloaded, make sure you download this repository to somewhere you will remember. Or you can select each of these and download them individually, but make sure you know where they are. I have them downloaded already in my directory. So what I'm going to do is in Altium, I'm basically going to import this new component library. So here, I'm going to right-click on the project, and I'm going to add existing, because this is an existing file. And then it should just open up your file explorer. And then here, you're going to have to look for that Git repository where you were initially. So I put mine in my GitHub folder, which I need to find. And then if you do so, you'll be able to find these two files. I would import both of them right now just for simplicity, but one of them, the one that's schlib, that one's for the schematic components. And then this other one, which is PCBlib, those are the footprints for the physical component when we are in the layout stage. You can import both of them. You really only need the schematic library at this point, but I will import both and press OK and open. And it should have added to your project. So you'll see this extra tab show up. You'll see libraries, and then you see two different folders. There's the PCB and the schematic library. Both of those should be in there now. Something I will note is make sure you put that repository link or wherever you downloaded those files in a spot that won't be moved later on, because if you move that, your project won't know where it's going to be referencing those components from, and you're going to have issues. It will get mad at you and you won't be able to find the components that you need. So yeah, go import that now, and I'll give you a little bit to do so. And if anyone's having trouble, let me know. Alrighty, all good? Perfect. Okay, so after you've imported these different libraries, I will show you how to put these on the schematic sheet. You can use the new part button, or you can use on the right-hand side, you might have this little components tab, and then you should see like the list of components that I showed you earlier. So if you click on, I'm going to click on new part, and then we're going to see this extra USB-C power supply schematic library file is now referenced in our project. If you didn't reference it before, this will not show up. Now it should. So if you click on that, you'll see a shorter list, but these are all the components that will be placed onto the schematic itself. This is what they should have, all the components. If there's one missing, I will update the file, but currently I believe this is what needs to be done. So to place a component, let's start with something big. Let's do the switching regulator. That's the LM2576 up here. Double click on it, and you can drag it into your canvas, essentially. And then I'm just going to place one of them for now. And this you can move around with the cursor. Each of these is a component symbol. You can create your own custom ones if you'd like. I've provided these just for to save time. Next week I'll show you how to make a very simple like resistor, but the concept will still apply to more complex components with hundreds of pins. So with this, I'm going to be following the same reference design here. As you can see, I kind of designed or drew the component symbol similar to how this component is laid out. So all the different supporting materials that you'll need are going to be the flyback diodes, the capacitors, and the inductors. These I am actually going to pull from the reference sheet. Where did my... So if you go to this week's file reference, this schematic document, this is what we're making. So we're not going to have enough time to do this in class just because it is more complicated of a design. So what I want you to be able to do is essentially replicate this sheet. You don't have to actually complete the sheet. I will provide you basically an updated file next week if you don't finish, because I know you all are busy, midterms are happening. So you can continue. I will provide basically the current project and what state you should be at so you can import it next time. But essentially, this is what we're building, so you can see how it mirrors the one that I presented earlier. So you have the input capacitors, you have the switching regulator, you have your flyback diodes, your inductors, and then this is an additional little filter on the outside. Does anyone know what that filter is called? It's an inductor and a capacitor. This is a pi filter, yep. So with the three together, it's a pi filter. It basically helps to, because this is a switching regulator, you're going to have a lot of noise coming off of this. It switches at like 30 kilohertz. You don't want that injected into your power supply rail, so you put this additional inductor and capacitor to form a pi filter, which helps reject more of that ripple. And then up here is a feedback network. This will essentially allow you to set the voltage that you're outputting. Yes?
On the pi filter, the values that are given there, are those order IDs or like manufacturer part numbers?
This is a manufacturer part number, yes. So compared to these resistors up here, which are 1K, that's pretty self-explanatory. This is a whole mess of part numbers. The reason being is sometimes there's a difference between specific and generic components. So sometimes I want to use this specific inductor because it has shielding, it has this footprint, and the manufacturer recommends it for this application. Sometimes, I don't care what it is. It's a resistor. It needs to be this big. It needs this value, so you just put 1K. So there's a mix of different types of values on this sheet. So like LED, I didn't put a full LED part number because I can just choose an 0805 footprint LED and it'll work just the same. But these capacitors, they have a specific footprint, and I've selected them just because this specific part is easier to solder than what we've done in the past. I have given a surface mount capacitor in the past. Everyone struggled with it. We're not doing that. We're doing a through-hole one because you can actually solder it in a reasonable manner. But essentially, you're going to be replicating all of this on your sheet. So I'm just going to go over like the different elements you can see as they were represented in the presentation. So you have your inputs on the left. So you have your primary and secondary supplies. So you can see there's like the little input jacks, the barrel jack, and the USB PD trigger board. So we're using an external board just to make it simpler because a PD trigger circuit is a little bit more complicated. They sell these little modules that are pretty neat. You just put it on your board and you get 20 volts. And then these are fed, so you can see these go into different flags. These flags will be fed into the switch, which is this component here. It's basically switching between 1 or 2 supplies for your input B. So power supply A, which is the top one, will always be powered from your primary. Power supply B will be powered by your primary supply or your secondary supply, depending on the position of the switch. Can anyone identify what kind of switch this is? Not by part number. DP double throw. DP DT. Yep. Mm-hmm. So there's 2 poles and they're ganged together so they switch at the same time. So this essentially allows you to separate the primary and secondary grounds from each other if you want one supply to basically operate completely independently of the other one but still be on the same board. So that's if you do like multi-rail supplies and you don't want your ground shared, you can use this to basically isolate whatever you're making. These are the output bleeder resistors. This is a pin header, so you'll be able to put like a little jumper on there, and that'll allow you to discharge the capacitors selectively. If you don't want it, you just pull out that jumper. And then here are the main switching regulators, which I've already gone over. And then the output, these are a bunch of different headers. So like on the right-hand side, this property window, you can see that these, that's great, footprint missing. But these are basically all the different headers that you'll have on the board that I showed in the 3D render. So you're going to replicate this. I will show you how to basically build that first supply really quickly by placing all the components down. So we'll go to the component selection tool, and then we're going to select all the components. So like the diode, we're going to select the potentiometer. The resistors are generic, so you can just put the 2 together. There's no difference between resistor. I think there's another resistor 1. They're the same. And then you can put the capacitor, which is that part number. And then the inductors. And then the other capacitors. Perfect. And then there was a tiny generic capacitor over here. Perfect. So once you get those all down, you can play around with them and arrange them how you'd like. I'd recommend following kind of what I've done before in the sheet, just because that's a decent representation. You can move these labels around. They'll still be tied to the component, but as you place them, you can like arrange things as you want. And then one thing to also note at this stage, everything has a question mark. So you can see like U question mark, L question mark, D question mark. Don't worry about that right now. You can manually fill those out, but there is a tool later on that we'll use that will automatically populate them, so it'll save you a lot of time. So you don't need to finagle with this value by double clicking and typing in your own value. So once you get all these components basically laid out kind of how you want them on your schematic sheet, you can just get to wiring them together. So a lot of clicking. And then don't forget to put your grounds if you didn't have that ground symbol before, so we'll just place some grounds. And then one fun trick is you can select multiple grounds, drag them up to connect the pins directly, which you typically don't do. But if you drag them back down, it'll automatically have the wire connected. Saves you a little bit of time. And then these are 1 kilo ohm resistors, so I'm going to change those values. Everything will appear in this properties window. This properties window is kind of important, especially in your layout editor. But here, what you're mostly going to be doing is changing your designator and your footprints in these. So if you select a component, you can select any of these components. You'll see it says designator, comment, a little description, and then in the bottom here, there's going to be these extra little details. So you can have your datasheet links. You can have the footprint render. So if everything is set up and you imported both the PCB and the schematic libraries, you'll be able to see oh, this is the 3D model for one of the components. So that's the switching regulator. And you can have a 2D, this is a footprint for that part. So I'm going to close that up. But here, you can edit all the different values. So these two resistors I placed down earlier, these are supposed to be 1 kilo ohm, but they're 3.3 on the sheet. So I'm going to select both of these because they're both resistors of the same type. I can change the comment on both of them at the same time. So when I type in 1K for the comment and press enter, it changes both of them. This does not work, however, for different types of components. It puts a star. If you type, usually they're both going to overwrite to whatever you put them at, but that's probably not the best because this is a resistor and that's an inductor. So make sure you're editing what you want to edit. I'm going to move all these. And then the final touch is I'm going to put the output flag. So this is, I don't remember what I called it. And then another thing, Altium is a modern ECAD software. You are allowed to copy paste. So this sheet is basically done, at least for the example. But let's say I want to have this interface with something else that I've already made from this sheet. I can go here and select a bunch of this, copy it, and then paste it. Wow, that's so neat. So if you do get stuck or you're behind, you can copy and paste from the reference sheet, and I believe it should just link everything together because they're from the same project. So as you can see, each of these has a representation already because it's linking to our libraries, which is the same part that that original sheet was derived from. And then one thing I forgot to mention is the sheet is kind of small compared to the reference. So as you can see, this one is an A3 sheet. This one is an A. So if you don't select anything, you can go to the properties window on the right-hand side and you can see sheet size. Change that to A3. That's what I use. You can make it bigger, you can make it smaller. So if you want like smaller A4 or an even larger A0, you're more than welcome to change it. But I would recommend sticking with A3. So yeah, that's basically the gist of what I wanted to cover today. So your task is essentially replicate the reference schematic that I put in the GitHub repo on week 1. If you can't finish that, I'm going to post where you should be at, so you can just download that new project file so you can continue off where we need to be for next week. Does anyone have any questions, comments, concerns before I wrap up? All good? Perfect. Yeah, so I'll be up here for a little bit longer. If you have any questions, chat with me or send me an email if you don't want to. So yeah, have a good day.